So if you watched the video, and if not, that's fine. It's not going to matter. I'm going to go over all of it. A vector has direction and magnitude. So it's what direction you're going and how far you went. So you're going to have these two component functions of the parameter t. It's not really different from a parametric equation. A derivative is still a derivative, an integral is still an integral. So this is not like actually new information. You just have two of them now, okay? So this is find the first and second derivatives of this, okay? So we're gonna find first derivative. And it has these like, not parentheses, but like, not brackets either. I don't know what you would call those, like a pointy parenthesis. Anyway, you're literally just gonna do the derivative of both of those. So what's your derivative for cosine? Yep, negative sign. So negative sine of t, comma, and then this would be 6t squared. If you're kind of like, that's it, yep, like a derivative is still a derivative. Like we're applying that to what's called a vector valued function, but it's not new information, right? Like some of the symbols are a little bit new, but that's really it. And then it said find the second derivative. So derivative of negative sine, well, derivative of sine is cosine, so it would just be negative cosine t, and then this would be 12t. So this says find the derivative at 1. So we're going to find the derivative first. And this is where, like, I may as well bring this up again since this topic is not too terribly difficult. We'll talk about this as well. About linkage errors on the AP exam. Try to put as few equal signs as possible, like to link things together. We're going to find the derivative, and then separately, we're going to plug in 1. If you were to link those two things together, they won't give you credit because 1 is the derivative and 1 is the derivative specifically at t equals 1. So just don't likely. When we did that last AP practice problem, didn't you guys do that? You like just didn't put equal signs? Like you listened to me and just leave them out? Yeah, it's a good idea. Just put as few equal signs. Do the whole problem and then go back and erase all your equal signs or something. All right, anyway, derivative of t would just be what? 1, comma, and then derivative of that second part, 2t. And then you're just going to plug in 1. So it would just be 1, 2. All right, now I'm going to bring up two vectors. So we've got one called v and one called u. So we're going to use both of these for the following question. d dt, and before it was d dx, now we have this parameter t. It's instructions that mean take the derivative of this thing. So what I would do first is like figure out what that thing is. So leave the instructions in there, d dt, and we're going to write what that would equal. It's 3 times v and then minus u. All right, so let's do the first part. We're looking at these two first parts. If we do 3 times v, 3 times this part, what's that going to give us? I'm going to do just the first part. You're right, but I can only do one at a time. Okay, so I'm going to just do these ones. Okay, so if we multiply it by 3, that would be 9t, and then we have to subtract this one. So what would that give us? 5t, good. You're doing 3 times this one, that'd be 9t, and then minus u, so minus 4t, that would be 5t. Now we're going to do the second one. So we're looking at these second parts. So we're going to multiply 3 times this one, that'd be 3t squared, and then minus this one would give us 2t squared. So it's 3 times v minus u. I just always do like the first parts and then comma and then do the second part. And then we're just going to do the derivative of that. So that would give us what? Yep, 5, comma, 4t. That's it. So again, d dt is instructions that mean take the derivative. So I would leave those in there until we figure out what this is that we're taking the derivative of. It's v of 2t. Okay, so we're not using u for this one at all. We're just using v. So we're going to plug in 2t per t. So what would that give us for the first part? 6t. And then the second part, it would be 2t in parentheses squared. So 4t squared. And then we're just going to do the derivative of that. So that would be 6, comma, 8t. I know you're like, this is super hard, right? I like these ones. All right, so we're gonna do the derivative of it, but it looks scary, doesn't it? Like if you showed this to somebody that didn't know what we were talking about, it looks really overwhelming because of all the symbols and everything, but what we're doing isn't actually too terribly difficult. All right, so this time we're only using u. We're not using v at all. We're gonna do 5t times u of t. So let's multiply these by 5t. What would we get for the first part? It'd be 20t squared, 5t times 4t, and then 5t times the second part, be 5t cubed. Perfect. And then we're just going to do the derivative of that. So that would be 40t, comma, 15t squared. Cool so far? All right. I don't love this next question, but I left it on here because I found it somewhere and I was like, oh, well, I guess I'll throw that in the notes. And it also brings up continuity, which we haven't talked about since unit 1. That was the very first unit, like first thing we did this year. So let's review what continuity is, because it's not going to be any different applying it to this. What are the 3 things you need for continuity? There is a what? Oh, you got 2 of them. There's a point, there's a limit, and they agree. Good. Teamwork. Perfect. There's a point, there's a limit, they agree. All right. So first, let's just plug in -1 and see what we get. And it's the same as you would do for a function. Like you would find f of whatever it is and just see where that point is. It's just we have 2 functions in terms of t. We have like an x of t and a y of t. All right, so if you plug in -1, you're going to get -1, comma 0. So that's what we got when we plugged in t is -1. All right, and then we're going to do the limits. So it'll be limit as t goes to -1 for that first part, comma, limit as t goes to -1 for the second part. Which is really, again, just symbols overload. Like it's just a bunch of notation. Because we're not going to actually do anything all that impressive with that. Just kind of looks like a lot. Because what do you get for this first part? If you do limit as t goes to -1 of just t, what do you get? -1. And if you do limit as t goes to -1 of this, you get 0. So did we prove that this is continuous? Yes. Do you see how they both came out to the same thing? Yeah, that was just really a review of what continuity is and a review of the symbols. I don't actually love that problem, but it's a good conversation to have to review continuity because it was months ago that we talked about it. So there's a point, there's a limit, they agree. These ones are integrals. An integral is still an integral, like an antiderivative, it hasn't changed. Okay, so we're just going to do the antiderivative of each of these. So look at the first one. What do you think? We're looking at just that part, the 2t minus 1. Good. T squared minus t. And I'm going to say plus c1 because there's going to end up being 2 constants here. And again, it's going to just really be a bunch of symbols where we don't really do much. Just I want you to see what the notation technically is. Comma. And then what would be your antiderivative for this part? That's a little tricky. So think first. But what would you get for that antiderivative? Very, very close. -1/3. Good. -1/3 e to the -3t. It's technically a u substitution, but I've tried to encourage you to, like, if there's a -3, just slap a -1/3 out front. If there's a 5, slap a 1/5 out front. Okay. Plus a constant, but it would be a different constant than that one, so we call it C2. You like that? C1 and C2? Well, now here's how we actually end up writing it, though. Or, I mean, I guess you could leave it that way. But you can take this first part, comma, this second part, and then just put it at the end as one big constant. And that's what's called a constant vector. I'm good with either way. I actually kind of like separating them better as well, because if they're technically 2 different numbers. But do you know how when we did the differential equations, and we said E is a number, C is a number, and we just wrote it out front as one big constant? That's like what that is. It's like we're just kicking it out of the problem and sticking it at the end as one big constant. Now, we won't have to worry about that in these two. Why not? They have boundaries. Okay, so we're gonna get like an actual value. Okay. But an antiderivative is still an antiderivative. What's your antiderivative for 8t? Be 4t squared such that 0 to 1, comma, and then your antiderivative for -3 would just be -3t such that 0 to 1. And then we're just going to evaluate this. So it's upper boundary minus lower boundary, but the lower boundaries are both 0. We're going to end up with just a value, which will be what? Yeah, 4, comma, -3. It would be minus the lower boundary, but again, they're just both 0. Let's try it again. I made this one a little bit more complicated though, so that we could actually like do a harder problem. All right. Cube root of t, that is t to the what power? Of 1/3. Good. Okay, so fun with fractions here. So if you do that antiderivative, you have to add 1 to the power, and we don't write 1 and 1/3. What would we put? Be 4/3. Good. And so out front, 3/4. Perfect. Such that 0 to 1. I always worry about how the fractions are going to go, but then you guys just kind of like didn't seem like you had a problem. Antiderivative e to the -t. Perfect. Such that 0 to 1. Now you have to be careful with the 0 on that one, because e to the 0 isn't 0, it's 1. Okay, so you got to be careful with that. The other one that you have to look out for is cosine. Cosine of 0 is 1. So like those are the two you really need to look out for, is e and cosine. All right, but this first part, 1 to the 4/3 would just be 1 times 3/4 would be 3/4, and then minus 0. And then this one, we're going to have to actually do both of them. So when you plug in 1, I guess you could write -e to the -1. I don't like negative exponents though. How could you fix that so it didn't have a negative exponent? Like if you wrote this, like, I mean, technically, but how could I fix that so it's not to the -1? Yeah, 1 over e, that just like makes me happier. All right, minus your lower boundary. If you plug in 0, e to the 0 is 1, but it would be -1, so plus 1, because it would be minus -1. And that's some value, because e is 2.718, blah, blah, blah. So this, I mean, if you type that in a calculator, you get some number. We'll do this one, and then we'll do a brain break. All right, so we're given the derivative, and then we're given an initial condition. Do you remember solving differential equations? You had an initial condition. Basically, if you plug in 0 for t, you need to make sure the first part comes out to 2, and the second part comes out to 0. So when t is 0, you have to make sure that this happens, okay? I usually just encourage everybody to do it kind of intuitively. So we're finding v of t. Would we do a derivative or an antiderivative for that? Yeah, antiderivative, because we have the derivative, we want to go backwards. So what would be your antiderivative for that first part? We're looking just at that. Why is it 2e to the 2t? Good. Like if there's a 2 there, you would want to slap a 1/2 in the front, but half of 4 is 2. Okay, now we just need to make sure that this ends up being true. If we plug in 0, we need to get 2. So if it isn't already, then we'll need to like add or subtract something at the end. So if we plug in 0, e to the 0 would be 1 times 2 is 2. Oh my gosh, it's good. So we don't have to do anything else. All right, antiderivative for this one. Yeah, 3e to the t, it's itself. Now, if we plug in 0, we need to make sure we get 0. So if we plug in 0 to this, e to the 0 is 1 times 3 is 3. But we need for it to be 0. So what would I put at the end to like turn it into 0? Yeah, minus 3. So you're just like doing that adjustment to make sure that this initial condition ends up being true. Does that make sense? Like if you plug in 0, you need to make sure it comes out to that. Now this other part, and I will give you a break and then we'll do this, but as a heads up, it's going to be a bunch of formulas that you're going to remember, and then you use them to do the motion problems. We're going to do more with the motion problems next time, but I just figured I would introduce it here because otherwise that's the entire lesson and there's just really not that much to that. So I figured I would at least show you this here and then we'll do more with it next time, like more practice. So these first three formulas are going to be like exactly like position, velocity, and acceleration that we've done before. Only difference is for some reason they use R for position. Do you remember what it was just with like functions, like not vectors? Like what letter they used for position?
No, it was S.
It was S, which doesn't make any sense either. Here they use R. I don't know. But usually they'll say in the problem, the position function given by whatever, and then the velocity function given by whatever. So they're going to say in words what it is. So the letter doesn't really matter like so much. But anyway, you have an X of t and you have a Y of t. And so, and it's cool to me. I like this. Like the X of t describes the motion left and right, and the Y of t describes the motion vertically. Whereas before we described motion just on a straight line. Do you know what I'm saying? Like now we have depth. It's cool. It's like a little bit more of a grown-up problem, right? So velocity is, you guessed it, the derivative of position. So you're just going to do the derivatives of both of those like we did on the other pages.
So like in reality, would it be like a phase of two? Or
For like a third dimension, we are not going to do that. But yes, that is a thing. And if you keep going through math, which in engineering, you're going to get to that, where you will do 3 variable calculus, where you will have, it's a XYZ plane. We aren't going to do that, but yes. Isn't that cool?
so like calculus C.
Well, in college, they don't letter them. It's calculus 1, 2, and 3. And it depends on how your college and your professor structure the course. I got to that in Calc 3. Some people do it in Calc 2. It like depends on, but it's one of the calculuses. It just depends on how they structure the curriculum. And then, well, I mean, there are 3 dimensions, so it's like a valid thing. All right, and then this is going to be the second derivative. So those all, logically make sense. Do you remember how speed and velocity are related? But velocity is directional. It can be positive or negative. Speed is what?
Absolutely.
Yeah, we did before, it was the absolute value of velocity. Here, it's what we call the magnitude of velocity. And again, what the formula does is it just turns it positive. It just doesn't use a square, or excuse me, I'm going to draw a square root in a second. It just doesn't use an absolute value. It looks like this. Because if you square something, it does what to it? Makes it positive. And then if you square root, you've like come back to where you were. That should remind you of the warm-up that you just did when you came in here. Okay. And then I should have made this its own line. I'm sorry, I forgot, but I'm going to put over here to the side average speed. Sorry, I should have made that its own line. So that speed, you want to do an average speed. Do you remember how to do an average value? Like when we did an average value when it was just the function f of x. Like if I said find the average value. Oh my gosh. Okay, perfect. Average value of f of x. It was 1 over b minus a and then integral a to b of the function. Good memories, guys. That's awesome. That makes me so happy because like, here's the thing. If nobody remembers that, then I have to go back and like reteach that before we can move forward. But if you all remember that, then we're okay. So your average speed is integral or 1 over b minus a, integral from a to b of all of that. And then dt at the end. So it's just like an average value, except instead of a regular old f of x function, which is boring, now it's a parametric or a vector valued function. You have an x of t and a y of t, like 2 separate dimensions there. Displacement and total distance. Do you remember what they were just when we did like regular old f of x functions? What was displacement? Well, kind of like if I start here and finish here, whatever that is, that's my displacement. If I start here and I run up the hallway and back and I end here, my displacement was nothing. But do you remember what the formula was? I'll give you a hint, there's an integral. What went in here? Or I guess I should make it
Square root
easy.
of something.
No, it was velocity. I'll just go ahead and tell you. What was the difference with total distance?
Yes.
We stuck an absolute value in there because we wanted all of the like accumulated distance to be positive. So like, again, for example, if I start here, run down the hallway, run back and end here, my displacement is 0 because I ended and started at the same place, but my total distance would be quite a lot. Okay. So it is the same thing with these. Your displacement, and again, you're gonna have those little like I need a word to call those, like pointy parentheses. It'll be integral a to b x prime of t dt. And then same thing, integral a to b y prime of t dt. And the reason it's the derivative is because that's the velocity. So it's same as before, you just have two of them. You have one for the x and one for the y. And the total distance, again, we don't use an absolute value. We use like squaring and then doing a square root because you have to include both the x in there and the y. So it's going to be integral a to b of all this. And if you're like, hey, that looks like the average speed, but without the 1 over b minus a in the front, it is, okay? Do you see how many of the formulas are that big square root thing though? X prime squared plus y prime squared. So whenever we got to AP review last year, it was really funny. Like whenever you get to a free response question where they ask you some of the stuff like, what's the speed? What's the average speed? Or what's the total distance? Everyone was like, oh, I can't remember it. And I would just go, it's the square root thing, guys. And then they were like, oh. So like if you get stuck, it's the square root thing, because that's what a lot of them are. Do you get what I'm saying? If you get stuck, it's the square root thing, just like the warm up that we did. All right, let's just try one of these. We'll do more of them next time, but I just wanted to introduce that stuff because today's like the actual derivatives and integrals, you already know how to take them. So I figured we'd do this too. So it's going to tell you if it's position, velocity, or acceleration. And typically they give you position or velocity. So you're given this, you have an x of t and a y of t. Find the velocity vector. All right, let's do that first. We're just going to find our derivatives. So what would that give us? Two t, comma, 1. Good. The acceleration vector. So we're going to do the derivative of that. Which would be what? Yep, 2 comma 0. Derivative of 1 is 0. And then an expression for speed. It's the big square root thing. Okay? Just draw it out blank. And it's your derivatives that go in there. Which, good news, we already found them. That's your velocity. 2t is going to go in this one. And 1 is going to go in that one. And then we're just going to clean it up a little bit. So what would that give us if we kind of like simplify, like do the squaring? I don't think nothing's going to combine there, but yep, good. 4t squared plus 1. So that's our formula for speed. Now we're going to do speeding up or slowing down, and I am going to like talk about that and lead you through it. But what I'm going to do is I'm going to pause the video, and I want us to get a graph of this so that you can visualize what's happening. Do you remember the quiz you took last time and I just graded it and handed it right back? Do you remember how the first 2 questions you made a T, X, Y chart and then that's what I'm going to have you guys do. So let's do times from -2 to +2. And I want you to fill in the chart. You guys can compare with each other and then just draw yourself a little picture. Okay. And if you make your grid about that big, you'll have enough space. So I'm gonna hit pause, do that, talk to each other, compare, hey, I got this, what did you get? Just so we can have a visual, because that'll help me explain some of the rest of this. The y values were easy because it just is t.
Yeah.
So remember, when you plot the points, you're not using t. Like the parameter doesn't show up on there. It's just x and y. So you kind of have to ignore this row. And if you didn't, go back and put the orientation on there, like the little arrows showing which direction it's going. Because that is important. We're like looking at the motion of it now. Did you all get a sideways parabola? So something like that. And I guess, I mean, I only gave you these t values. I guess it would like keep going, but it's going like this. Are we all together? Okay, the visual is going to help when we go to explain this. So let me review how we did speeding up and slowing down back with just regular old f of x functions, you know, back in the day. How did you do whether it was speeding up or slowing down? This is a tricky one. This one does tend to get people, so that's why I want to review it. Oh, velocity and acceleration are the same or opposite. What does it say? Oh, speeding up or slowing down. Huh, so I guess I brought them both up. So speeding up would be they are same, slowing down, they are opposite. But you have to look at both, and that's the thing is people will look at one or the other and forget to do both, okay? And it's the same thing here. So let's look at our velocity vector at time t -1. I always say time, it's technically just like, because it's t, I always say that. I guess you could call it time. All right, so plug -1 into our velocity vector, what would we get? -2, 1. And then plug -1 into our acceleration vector. There's actually no variables there. It would just be 2, 0. I'm going to color code this. The colors don't show up real well on the projector, but when I take a picture and post it on Schoology, it'll be there. We're talking about t being -1. That was this point right here. So -3, 1, that's this point. Are we coming together here? You're gonna have to look at it. So this is the point we're focusing on. That's where the particle is at that moment. Velocity is pulling us -2 in the x direction, +1 in the y direction. So from this point, you would go -2 for x, +1 for y. Do you see how we would start here, go -2 for x, +1 for y? So your velocity is that away. It's a vector. It has magnitude and direction. Okay? Acceleration from this point, what is it doing for x and y? 2 for x, nothing for y. So it would just be like that. So if velocity is going that way and acceleration is going that way, do we think speeding up or slowing down? Slowing down. And that's your reason why. So you would say slowing down. Do you see how the visual helps? I kind of need to see it. Slowing down at t being -1 because I would write it out in words actually. Velocity and acceleration vectors have opposite directions. And don't stop listening because I want to explain one other thing. It should make sense that it would be slowing down at that point because watch, as your particle goes along, what's it now going to do? Right. And in order to make a turn, you would, in theory, I guess, unless you wanted to tip your car over, you would have to slow down. Okay. And I'm just going to add one more thing. I didn't leave a lot of space. I wrote too big. Your constant speed, like cruise control, would have your velocity and acceleration vectors doing something like this. Like at a right angle. That would be a constant speed. So neither speeding up nor slowing down.